Okay, you did that.
So, okay, so we will continue our discussion on software reliability. So we were looking at software reliability, and so we had looked at some of the concepts like the operational profile, modeling reliability growth, and we looked at the exponential reliability growth model. We looked at the underlying assumptions. And we looked at the significance of the two parameters. And also we looked at the logarithmic model. And I mentioned the fact that logarithmic model sometimes fits very well, although the significance of the parameters is not quite as straightforward as we have for the exponential model. And then we were talking about how do you compare alternative models, and that is actually a question that comes up whenever you are evaluating alternative empirical models. Now, software reliability growth models, sometimes they are purely empirical. You think, maybe it will fit this mathematical expression. But sometimes they are actually derived based on some basic considerations, so some assumptions, and then you derive them. Either way, sometimes they use a combination of the two. So we were talking about comparing models, and I was mentioning about average error and average bias. And you can make plots of average error and average bias and see how the error, so eventually the error should approach zero as you have most of the information near the end. But of course, significance of the predictive capability would be, predictive capability is actually important in sort of earlier durations of testing. Because by the time you get to the end of the testing, you more or less know most of what is there to know. And we had seen that the logarithmic model does well in terms of average error and average bias. Inverse polynomial model, which is a model proposed by Littlewood, it does well. The exponential model is okay. The S-shift model, we examined collected a number of data sets from a number of different sources. So some of the sources, some of the data was collected at AT&T by John Musa. Some of the data was collected by some researchers in England. Some of the data was collected by some researchers in Japan. And so we looked at, I think, 10 or 12 different sources of data, 10 or 12 different data sets, and then we came up with our conclusion. Okay, so how do you use an SRGM? And we were talking about that, and you had done something in the assignment. So basically, before you start testing, you can estimate the value of beta 0 and beta 1, although probably not very accurately, especially with beta 1, based on your past experience. And you can decide how much testing you need to do before you will achieve the target reliability level. Now, when you have started testing and you have started getting some data, then using that data, you can make a prediction. You can fit the data points to a model and see what the model suggests, how much more testing you need to do in order to, there are typically two different targets. One is the defect density. So when the defect density, when the predicted defect density drops below a certain level, or when the defect finding rate, when the failure intensity drops below a certain value, then you would decide that your software is now reliable enough. And so any questions or comments? Okay, so let's go to the next topic. Now, I had briefly mentioned about module size distribution and defect density. And I had mentioned about optimization. Maybe we can go back a little bit and take a look at it. So I think the slides are available. So this is some work we did, and basically we were looking at how defect density varies with module size. And we proposed a model. So this is a oh, did I leave my stapler here? Oh, I seem to have left my stapler somewhere a few days ago. And maybe somebody took it. Okay, I guess maybe I'll have to get another one. Or did I leave it in the other class? Probably in the other class. Anyway, if it's gone, I guess it's gone. Defect density and module size. So I was mentioning about it, that the fact that there is evidence, if you collect all the data sets that have been become available, the defect density declines. Defect density is higher for very small modules, and it is also higher for very large modules, and there is some optimal module size. And we came up with a calculation of module size, and some people like this idea and they have put it in a textbook on quantitative software engineering. So I thought that you might find this interesting. So here's our model. So basically, we in our hypothesis, we suggested that there are two different types of faults. One of the faults are there around the surface of a module. That means they deal mostly with interaction of other modules, and we call them module-related defects. And then there are some defects that are within a module. So we call them instruction-related defects. And let us say that we have total defects per module is A, and module size is S. And we assume that these defects are uniformly distributed among the modules, regardless of the size of the modules. And so we say ds, d sub m, a function of s equal to a by s. So if each module has about equal number of these interface-related defects, defect density would be the number of defects per module divided by the module size. And then you have instruction-related defects. And I call them d sub I. So here we assume that these defects are, now if you assume constant defect density, this would be just a constant. But if you assume that there is a linear growth for larger modules, the defect density should be slightly higher. You add a linear term, and probably the C might be small. So with the composite defect density then, total defect density would be equal to the sum of the two kinds of defects So notice that now this function would have a bottom, and as you know, you can get the minimum defect density. So this will give you for minimum. Okay, how would you obtain minimum defect density? You take the derivative of this with respect to S, equate that to 0, and solve that, and solving that you will get the minimum defect density would be equal to square root of AC plus B, and optimal module size, so that is the optimal, E by C. And basically what you will notice that as a result of the combination of the two, things would be like this: size and defect density. And at this value, which is given by this, and we have plugged in some numbers, and I have some numbers here. And after plugging in some numbers for various data, we found that, for example, here is a data by Withrow, where A is about 121, B is about 1.76, C is equal to 0.0063. Notice the C, value of C is small. And actually, notice here that this effect is actually fairly pronounced if you look at the data. But this rise is actually not very pronounced. So for large modules, defect density does not really grow that fast. And basically you get S min if you plug in the numbers, or if you look at the plots, it's approximately 200 lines of code. So this would mean that 200 lines of code is about optimal. Now, we got a lot of objections to this, because some people said, no, we have been told that the module should be as small as possible. That is the modern approach, and of course we didn't find any evidence to support that. All available evidence supports that very small modules are likely to have high defect density. And then this is also I was mentioning. Then we thought, okay, so this is for individual module, but in a given project, your modules tend to have a certain distribution size, and we had discussed this earlier. And since we are now looking at some mathematics, why don't we take a look at it? Now, we looked at some module size distributions, and I have a couple of plots here. So here is a GNU-C library. So Jason Denton, who was a student, so he looked at the GNU-C library and found the sizes of all the modules. And we made a plot of module size versus the module count. And to our surprise, the plot was like this. And we looked at some other data. Some other people have given data. And this seems to be the rather common pattern. So this is a large number of small modules and a small